But today, my hat is Max. And so I'm the manager there, and I want to talk about how you can design materials using high-performance computing. Essentially, our center is very similar to the one, organized very similar to the one, Irving is one of our PI, so he copied our organization upside down, I don't know. And so I don't want to repeat, and I'll concentrate more on the problem and on our strategy. So, as you know, materials are the way with which you interact with innovation. All the innovation that you use are made of materials, and this is the interaction that you have with innovation today is made with materials. So you have to have a way to understand what materials can be used and in order to innovate your environment. And originally, I mean, materials are very important in the human history. There is the Stone Age, then Bronze Age. You know, Stone Age is a wrong name, by the way, because the right name was been Wooden Age. Most of the manufacture at that age, 99.99% was made by wooden, not by stone. Only that we have looked, we now only find the stones, and we call it Stone Age, but the real word would have been Wooden Age. So the material there was wooden. And so material has really described our evolution up to now. Now we are in the silicon age. And in fact, we use computers to project new materials. And originally, you find the materials, and then after you find it by some causality, then you think how to use it in real life. Today is mostly upside down. And you think a functionality, and then you look for the material. But still, this is a very creative process. And we, together with them, and we still have to maintain this possibility of the creativity inside the discovering process. So our centers, if we want to have an impact in the discovering process, in the innovation process, if we want to have an impact, we have to maintain the idea that this is a creative process and should be designed. Our centers should be implemented in order to allow people using our programs in a creative way. Okay? And just as an example for creativity is the famous Post-it. Post-it they were at 3M. They were looking for a very strong glue. They were very hard pushing for looking for a very strong glue. And then they found the glue that was not strong at all. But then they used it, and then they invented the Post-it because of that, because the glue was having a particular thing, so it was not leaving any halo on the paper. So the change in the idea of the functionality was embedded in the process. And this is crucial. This is crucial in order to maintain creativity. And this is because the future is unknown. So in business, processes are more relevant than targets. This is something that I will always repeat to my collaborators. Processes are more relevant than targets because targets are moving. The future is uncertain. And, Keynes taught us, and also Hayek, by the way, taught us how can we take decision under uncertainty. We can take decision under uncertainty if the decision process, if uncertainty is embedded in the decision process. So the crucial point is that we have to design our system, our way in which we interact with the users in order that this opening is inside, the uncertainty can be coped with. And more importantly, our users, for them, is more important to find the right questions than to find the right answers. We have to help our users to find the right question, because the right answer to the wrong question is useless. The right questions is the most important thing. We have to design a system, we have to design a process in which our users can help to find, that for the managers and so on, the right answers, the right questions, and we have to focus on the questions. So today we are in the silicon era, I said, and there are these computers that are advancing very fast, and we are in this exascale, exabyte, just to remember that also the size of the data are important, and for us it's very important. The data, we embed the data inside HPC thinking to workflows, okay? And I will show you, I will explain you soon how we do it. But so concentrating on workflows. The idea here is that there is quantum mechanics, and there are fast computers, so you can look at new materials using quantum mechanics and fast computer. CP, the two guys, Karen Parinello, that for us is really, there is a pre-Karen Parinello era and after Karen Parinello era in material science. And the two guys were so smart to combine quantum mechanics to treat the electronic properties and classical mechanics to treat the atoms. Because the atoms, as you learn, they oscillate at a frequency in which is useless to use quantum mechanics for silicon that is too heavy. Quantum mechanics has no effects, okay? But electron has to be treated in quantum mechanical way. So the idea of Karen Parinello was to combine the two in a very smart way, and from then, now there is the possibility with CPMD and all the program that I will show you in a second, at that time, the first work that came out from that group was from myself on material science. We were studying the diffusion of a proton inside a silicon wafer. And so the idea is that using this kind of approach, you can really try to understand what is technologically relevant and to design materials. But of course, you need very large computers to be effective. And HPC probably will be the solution. So what we want to do in Max is that we want to speed up the innovation cycle. We would like to collaborate with industry, startups, etc., with the industrial ecosystem, in order to speed up the innovation cycle. So we started, as they start from 3 codes, we started from 5 codes, they are there. Quantum Espresso is the code that embed now the Parinello, the code that I wrote when I was young, is a very popular code. When we presented to the community in 2010, now is a code that is that paper has about 9,000 citations, okay? So that tells you that there are a lot of people using it. And in fact, the community, so our idea is that we want to have a center that is user-driven, in order to speed up user-driven innovation with result-driven innovation. We want to use the open software paradigm because we believe that open software is the solution. And we want to focus on an industry-oriented solution. And this code, the AIDA substrate, is a Python embedding with which all the code can communicate, because it is the part that is attached to the data sets, okay? So all the codes do communicate with AIDA, and AIDA can communicate also with other codes. And so it's a sort of a scientific bus in which you put all your apps, Quantum Espresso, yes, all the interface, eventually other interface for visualization, etc. And so this is the substructure on which we that help us to move, to work on the workflow, to manage very large amount of data, to be how to say to sanitize data, okay, in order to have the best data for the best representation. And so we started with a strategy, as I said, very similar to the one described by Erving. The strategy was what we call code first. Of course, you have to start from something when you want to build up such an environment. And to start with, we started from codes. That was the first code. But now, that was a year ago. Now we are at the zero time. We are moving from a strategy that is code first to a strategy that is service first. So we are now concentrating on service because the service are the way in which we will interact with our customers. And we are developing together with BioExcel and with Combiomed and other centers of excellence. We are collaborating in understanding the business models that can be implemented on this kind of services, okay? And so the first service that is up and running now is a portal in which there is an help desk, it is thought to be very user-friendly for people that are using code much than before. And the next step is what we call quantum as a service, and will be ready in a year from now, so to speak. That is an easy to deploy and easy to execute virtual machine-based service that can be executed on federated HPC center or commercial clusters. In the meanwhile, we are, and of course that is based on AIDA, because AIDA is what is able to move all this data from one side to the other, running program, and so we have this substrate that is crucial for our program to communicate and to be executed on that centers. And then we have a few kind of, we have some pilot projects that we help us to understand the user needs and the optimal solution in an industrial context. And so it's two proof of concept. One is the realization of another layer of abstraction in which the code do communicate again one with the other, but in a more integrated way. And the other one, and while we have a realization of what we call material intelligent analytics that is driven by Professor Laio in Trieste, that does something similar to this community here. You have an enormous amount of data, and data they in fact work in medicine and in social science. Data are not homogeneous, like you want to combine computer data, simulation data with other data, etc. And then they found a way that the work was published on Science in which you can clusterize this data very efficiently. And then once you have clusterized the data, once you clusterize the data, then you categorize the data, and the data can be understood, okay? And so this is another proof of concept that was already running on materials. And then there is a demonstrator that is the implementation. We want to explore the HPC feasibility of our code up to petaflops or whatever. And what is our ecosystem, what we refer to? The ecosystem, of course, are the innovators, the entrepreneurs, the researchers, the scientists, the engineers, the software engineers, the vendors. We have a number of interaction with the vendors of this kind of solution that implement our solution inside their the selling proposition. Of course, the HPC center, the HPC industry, and the other COE like you here. And in numbers, these are the people that do participate to the institution that do participate to MAX. KTH is one of that. You just heard the presentation before. Then there is APFL, CINECA, CNR, etc., BSc. So we have essentially 5 research institutions, 5 supercomputer centers, 1 global education institution, because for us to educate people in using these things is crucial, particularly in the third world. And so we choose UNESCO and ICTP as the partners for this. Then we have 2 business partners, one more focused on hardware solution, and the other one most focused on business models. Then we have, as I say, the 4 flagships, one platform for workflow data sharing and data management, dynamic data management, and we have at least more than 10,000 users. The pilot project that we are implementing at the moment are 4, and has to do with lithium-ion battery, with Bosch, Mars, with food colorants, lubricants is Total, and this is Total plus Toyota, and the heat storage is a Spanish company that is working on that. Now, this is my last slide, so we can go to lunch after that. And I want to show you here the complexity of the problem, of the challenge that we are going to face. This is my program, CP.X, that is part of now of the Quantum Espresso suite. And these are the scaling benchmark now up to, there is not a pointer, but essentially here you are already in the 2-3 petaflop range, okay? And the petaflop range is not peak here, is not sustainable, is not sustained, is real application, okay? So we are able to reach with 64,000 core, we are able to reach real applications in the petaflop scale. Of course, exascale will be 1,000, but the exascale possibility will be not now, in 23, 24, something like that. Okay, so but still we are working on that, and then we will see that we are approaching so this is the good news. The bad news, at least, bad news always shadow some opportunity. The bad news is on the other side. The other side shows that if you scale your programs, then with number of cores, then there is the performance can go very good, like here, or very bad. You see all this scatter of the problem. And this is because the system is very complex. And the network that is behind the cores may have some bugs. At the end, in this kind of computer center, you will have something like 10 to the 18 transistors, okay? So you are very near to an Avogadro number of transistors, not far too much. And that means that the statistics start to playing a role, okay? You have not to think to this computer, and they are they are even dishomogeneous. So you have to think, so in the past, a computer was a computer in which every node should do something that is very predictable, very clear, very mechanical. Now that the numbers are so high, you have some nodes that are eating too much, for example. The heating system is really problematic. Next year, in Argonne National Lab, there will be implemented a HPC computer that will have a peak of 150 petaflop, okay? The power consumed by that computer will be 13,000 kilowatt. That is a significant part of a nuclear powering plant to run a single computer, okay? So it is a significant part, it's 2 to 4%, of a small nuclear power plant. So it is this kind of computers, of course, they use a lot of energy, and they heat up in a very dishomogeneous way. And that means that you have to take that into account when you want to when you want to perform. So even your algorithm, even your theory should now be written in a way in which you manage these kind of things. For example, in Carparinello, that you can, when you do quantum mechanics, you can or make a minimization or make a dynamics. If you make a minimization, you have some plus. If you make a dynamics, you have some other plus. But now it looks like that if you make the dynamics, this kind of dynamics are more efficient on that kind of computers because they distribute better the memory. So it's what we call this co-design. Our program is used by the Defense Department of Energy in the United States in order to test, by Intel, in order to test the performance of the new design CPUs, okay, and core. So it is, and we collaborate with them, in order, and also they are doing, because now it is crucial that the application, they are designed with respect to the performance of the computers and the performance of the computer, the network of the computer, the design of the computer is combined with the application. So we call this co-design. And co-design is a crucial part of Max because we want to go, if we want to take the exascale, if you want to go to the exascale, this is necessary. We have to think your algorithm, even your theory, in order that is more efficient on this kind of computer. But you also have to design your computer in order that this kind of and so all these centers are there for this reason. Are there in order they want to combine users with the HPC center, but also there because if we want to take this challenge to go in the direction, this is the last slide really, and to go in the direction of the exascale, you need an effort in this intermediate. So a single researcher cannot face this. Even if for a group is difficult. You need to have a center of excellence that helps these groups to go in that direction because of the co-design, because of the difficulty to program and run programs, as you said before. That's here. If you run the program without making any optimization, you end up you don't have any scaling. You even get the worst. This on the right part, okay? You get even worsening your code, but that is because the system is too complex to be faced with all computational techniques. And so our vision, that this is the end, is that we imagine a future in which computer simulation are at least 1 time faster and more workable than today. And in this way, we are sure that we can discover new materials, we can get new ideas, we can produce new applications. We all the people around will produce new applications by scientists, designers, and entrepreneurs. Thank you so much.